Hi everyone. On this video, this is more intended to be a review of some of the concepts in the chapter. There are some notes here and some examples. I would like for you to watch the video, take notes, and you can also go back and add some of these conclusions to some of the notes we've taken before. So let's get started. So first of all, I want to talk about the interpretations and applications of the derivative in the definite integral. And so some of this, of course, you should have the notes page once again, but it says that the derivative of the amount is the rate at which an amount is changing. And remember that rates are usually measured in feet per second or something like that. For example, if water is being drained from a swimming pool and the function r of t represents the amount of the water measured in cubic feet, at any time measured in hours, and the derivative would represent the rate at which the amount of water is changing. So in other words, here's the notation, this means this. So what would the units of r prime of t, and it said that it was cubic feet per hour, so this would be feet per hour. Cubic feet per hour. So if we talk about the integral, right, from a to b of the rate which is with the derivative, would be the amount of change that you would have seen from the beginning. Now, if there was already water in the tank, then to determine the amount of water after the change, you would actually have to add the initial bit of water, which we'll talk about here in a second. So in the context of the example above, what does this represent? Well, this represents the amount of change I'm going to abbreviate if I can. The amount of change in the water level from time t equals a to t equals b. And so that's what this notation means. So here's another example. It says the table given below represents the velocity of the particle at given values of t, where t is measured in minutes. And so here we've got your different t is in minutes, and v of t is feet per minute. So that's a rate. This is a derivative table. It says approximate the value of the integral from 0 to 30 of v of t dt using a midpoint Riemann sum. All right, so midpoint Riemann sum I'm going to do down here, right, because we're going to go every 10. So you would do 10, and then you would determine 1.6 plus 3.1 plus 1.6, and that would equal approximately, no, exactly, sorry, 6.3, let's see, so that would be 63, and that would be in feet. All right, and so this is the amount of change. This is the most important part, right? Because we've done the table with the midpoint Riemann sum, but we're trying to figure out, what does this mean? What are we finding when we take the integral of the velocity from 0 to 30? And it's the amount of change of position of a particle from t equals 0 to 30. And so then what is the value of the integral of a of t, acceleration, from 5 to 25, and explain what the value means? Okay, so if I use the notation, I would say that the integral from 5 to 25 of a of t dt is going to be equal to, if you take the integral of the acceleration, you get velocity. So this would be the velocity, and it's a definite integral, so velocity from 25, sorry, that's a 5, to here, which if you look that up in the table, v of 25 is 1.6, v of 5 is also 1.6. So 1.6 minus 1.6 is 0 feet per minute. And so this just represents the amount of change of velocity. This is the verbal component of the particle from t equal 5 to t equals 25. So the next thing we want to do is tie together this idea of average velocity and average value of a function. We talked about average velocity before, average velocity. And remember that we found it to be approximately the position function at B minus the position function at A over B minus A, right? And remember, we could have said A minus B, right? We could have switched that order, but I want it this order for particular. So we find velocity by finding the average of the position function. Remember, it goes position, velocity is the first derivative, and then acceleration. Okay, that's the order. So if you go this way, you take the derivative. If you go this way, you're going to take the integral. All right? So if we're finding average acceleration, then, of course, we're going to use velocity, v of b minus v of a over b minus a, same order, right? So if p is the position function, and v of t is the velocity function, and a of t is the acceleration function for any time t, then how could we write an equivalent expression for the following integrals based on the fundamental theorem of calculus? Well, if you look at this, right, if you take the integral of acceleration, you get what? You get velocity. So this would be 1 over b minus a times v of b minus v of a, right? So this is equivalent to average acceleration. This is the average acceleration, right? Because you're finding this. They look exactly the same. And vice versa. On this bottom part, I have now velocity. Well, the integral of velocity is position. So b minus a, and then this is p of b minus p of a, and this is equivalent to average velocity. So therefore, the average value of a function f of x on an interval from a to b is defined to be 1 over b minus a from a to b of f of x dx. Now, f of x might be the velocity function. F of x might be the acceleration function. It doesn't matter what function it is. This will find an average value. Now, this is an average value. It is not an average rate of change. Average rate of change is always a derivative, always the slope of the secant line. But this is average value, so it's going to use integrals. All right, so to do a problem like this, here's my f of x, here's my interval. You would use a calculator to determine this. And remember how we do a definite integral on a calculator. All right, so I have 1 over b minus a, which is going to be 3 minus 1. That comes from the interval. And then the integral from 1 to 3 of my function, f of x, which is x to the third. And if you take one look at this, this is not a fun function. It is also not integrable. I love that word. Using u substitution or any integral method that we know. So you would have to use it in a calculator. And so if you did that, you would get 1/2 times 11.696, which is equal to approximately, because it's rounded, 5.848. All right, so an average value of this one using a calculator, this would be non-calculator, same formula. So I'd have 1 over 6 minus 2 from 2 to 6 of my function, 2 minus 4x dx, okay? And so I'm going to, that would be 2x, going to integrate, and then this would be 4x squared over 2, which would be 2x squared. And I want to do this from 2 to 6, 2 to 6. And don't forget, I'm multiplying all of this times 1/4. That's this. Don't forget that part, people tend to. Okay, so that's going to be 12 minus 72 minus, in parentheses, 4 minus 8, right? So this is going to be negative 60 plus 4, and it's at this point, once again, that we're going to forget to put that 1/4. Don't forget the 1/4. And so this is going to be equal to 1/4 times negative 56, which is, believe it or not, negative 14. So now you have one example where we used a calculator because it can't be integrated, and another where we did not. So our final example uses a table of data, but we need to know what's in the table and interpret it, because we have an x, we have f of x, and we have a big F of x. So what it says is that f of x is continuous, and f is the derivative of big Fx. Okay? So if I have, think about this, if I have big Fx, then derivative of that would be on this side, right? Whereas, you know, where you had the function, you had the derivative, and you had the second derivative, right? So it's saying that f is the derivative of big Fx. So it goes this way. So if I integrate this one, I get back to big Fx. All right, so what that says is, in a definite integral, is that since I have the derivative and I'm integrating it, I get back to big Fx, so it'll be big F of 3 minus big F of 1, which I can get from the table and find an answer, right? Because big F of x of 3 is 8, and 1 is 3, right? So this would be 5. So knowing this, see if you can work this next problem, figure out what it is, and be sure to ask me in class if you have the correct answer. Okay? So I hope to see you there with the correct answer all worked out, and I'll see you then.